can't make bloopers. No,
You're making a Mickey.
We will be presenting problem number 58.
Bloopers? But if you're not funny, you can't just start with your bloopers.
According to the problem, we have two parallel plates. The top is and obviously, since we have charges here and charges here, at any point in between these two plates, there must be a force. Like if we put a charge in between these two plates, it'll experience a force. So we know there's going to be an electric field. A couple of things to notice immediately. The electric field, since we have two plates, it's not quite constant, but we can assume that it's constant. And that's just by nature of there being two plates like this. So the electric field is constant, and that means that if we put a charge here, a charge anywhere in between these plates will experience the same force. That is, the force is constant, which is a good thing because that means that's kind of an indication that later we can use energy considerations. So we have a particle going in between these two plates. It's an electron, so it's negative, and it has a velocity in this direction. We don't know what the velocity is. You should note that it's an electron, which is a negative charge, which means it's going to be pushed opposite to the electric field. So the electron is going to, it's going to go something like this because it's going to experience a force in this direction, right? So the problem basically asks what the maximum velocity is that we can put on this electron before it hits this plate. So if we envision the path of the electron, it's going to start here, it's going to go here, it's going to stop just before it hits the plate, then it's going to start getting pushed back this way. So that's going to be the path. And again, we know that there's a constant force, so that indicates that we might be able to use energy considerations because, as we know, work is equal to force times distance. And since there's a constant force, we're able to use this one. And we also know that the electron has kinetic energy to start off with, and no other energy. It has no potential because it's starting at the positive charge. So we can, in keeping with energy considerations, we can basically maintain that the work that we need to do to move the electron from here to the plate. And also notice that, even though the electron is moving in at an angle that's actually 45 degrees, the angle doesn't matter. And they also give you a length for this, 6 centimeters, but we really only need to know this length, which is 1 centimeter. Because the field is going in this direction. So any work that this field does, force times distance, and it has to be in the direction of the force. So any work that this field does can only be in relation to vertical distances. So that's important as well. So we don't even need to consider this distance. We just need to consider this 1 centimeter distance that it's moving over here. And so that's the conceptual background.
YouTube video.
We can use the work-energy theorem to figure out its initial velocity here using the distance here. So it has kinetic energy right here, which is equal to 1/2 mv squared. We need to find this. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. And the charge of an electron is 1.6 times 10 to the negative 19 coulombs. So here you can bring the 1/2 over to the other side, divide it by and take the square root. And for F, you use the uniform field formula, which is E times the charge of the electron, and multiply it by d, which is 0.01 meters, and divide it by the mass. Square root all of that to get your initial velocity, which would be 4.2 times 10 to the 6 meters per second.